Questions from the homework from last day, lesson 6, number 5. What happens to the voltage drop across the 5 ohm when it's closed? Does it increase? So when it's open, this isn't even part of the circuit. The total resistance, I have 2 resistors in series, the 20 and the 5. What's the total resistance? What's the total voltage? What's the total current in your head, please? So with it, I'll make a little note here, open. With it open, I have 4 amps going through here. How many volts? Okay, V open is a 20 volt loss. 20 volts go through it. Now, let's close. Now if I close, these 2 are in parallel. So first I'm going to have to find R parallel. That's going to be 1 over R parallel equals 1 over 5 and 1 over 10. What's the parallel equivalent of those 2? One divided by 5 plus 1 divided by 10. That's the same as a, don't forget reciprocal, 3.3333 ohm resistor. Is that okay? In other words, I can replace these 2 here with 1 resistor of how big? 3.333. Normally I'd redraw this, but I don't have enough room. So if that's the case, when it's closed, what's our total? I think it's 20 plus, 3.3. Is that okay? All right. So that means what's the total current? 100 divided by 23.3. Yes? So plus 20. 100 divided by that. 4.285. I'll go 4.3. But I'll keep that number on my calculator. Yeah? That's how many amps leave there when it's closed. How many amps in this top resistor when it's closed? You know what? Stay blue, Mr. Dueck. Now, let's try and generalize from here, okay? What do you notice when I close the switch? When I add a resistor in parallel, what happens to total current? Increases. Does total current flow through this resistor? So what happens to total voltage in this resistor? And since I have 100 to start out with, what must happen to total voltage here? Decreases. That's actually the answer to number 6 if you're trying to talk about brightness and voltage and power. But I'm pretty sure if I actually crunch the numbers as well, it's going to be 5 times... Hey, the voltage now is... oh, hang on, Mr. Dueck. It's not 4.28 in each one. Good gosh. Let's try that again. Dueck, you botched that. You were doing so good. 100 divided by 23.33333. Okay, so there's the current. The current splits up right here. Some goes this way, some goes that way. So I can't assume that 4.28 amps goes through there. I can say, okay, times by 20. The voltage that I have in this top one is 85.71. 100 minus, careful, Mr. Dueck, 100 minus that. That leaves me with 14.28 volts through this. And that is a legitimate ski run. I can't get to the bottom. Okay, so that is the correct voltage. And with the resistance of that, now I can say divide by 5. You know what? Only 2.8 amps are going through there. Well, of course not all. Some of the current's going to be going that way. That's naturally going to, since voltage is I times R and R hasn't changed, naturally, now that I think about it, yeah, the voltage is going to drop there. Is that okay? So what happens to the brightness of the bulbs in this circuit? This now has, because you've added, that lowers, that increases So that's going to make that brighter. Why? Because power, in terms of current, is I squared R, and it now has more current going. The resistance hasn't changed. It now has more current going through it. Oh, and it's going to be dimmer. Why? Because a whole bunch of the current is going that way. Its I squared R has gotten smaller. Oh, and this is going to be on in the first, where it was non-existent before. Now it's going to have some brightness. And you could actually crunch numbers if you wanted to prove it, but there's a more, not even an algebraic proof, a theoretical proof. This is why I said last class, when you add another resistor in parallel, trust me now, our parallel just got smaller, which means our total just got smaller, not bigger, which means I total got bigger. Is that all right? Yeah. It's a great question. Any others? Today we're going to be finishing off the unit. Today I have a take-home quiz for you. Today I have the great big ultimate unit review for you. Wednesday is going to be mark the take-home quiz, press pause. Okay? I think right now your test is going to be a week from Wednesday. Is what I'm looking at. So I'll probably do a tutorial next week, Monday. But I'll send an email out to that effect. Oh, and nope, never mind. Pause. First of all, can you take a look at the ultimate review that I just gave you? There's a couple of questions we need to nuke. So take a look at this. Number 3, transformers are going to be in a different unit. So cross out number 3, Nate. Cross out number 3 on the review. That's fine. There's one more. Where is it, Mr. D? That's all good. That's all good. Looking for the one that talks about power being shipped through power lines. We're going to look at that on a... Oh, did I miss it? No. That's good, good, good. Number 40, cross out number 40. I think that's it. 3 and 40. Yeah. So, lesson 7, let's finish off the unit. So take-home quiz next class. We're going to get a bit more specific here. Today, finally, and I think somebody asked this question, I think it was in this class, someone said, hey, Mr. Dueck, don't batteries actually have resistance? Actually, they do. Up until now, our batteries have been perfect, and there's no such thing. So this lesson is called terminal voltage. Terminal voltage, you guys with me? Okay, guys, you gotta be with me now. This is an important lesson, and kids struggle with this. Terminal voltage is the actual voltage you're getting from the battery, not the theoretical. This battery says on it 1.5 volts. You're never going to get 1.5 volts from it. If you connect it to a voltmeter with no current flowing, it'll say 1.5 volts. But as soon as current starts to flow, you lose a tiny bit of voltage. Show you what I mean. Read along with me. It says, this is the voltage or the potential difference between the ends of a battery or cell. The ends or posts of a battery are called terminals. And a cell contributes some resistance to a circuit. This is called the internal resistance of the cell. In other words, here's a battery. In a circuit diagram, we have this. The EMF, that's this thing right here. This is the symbol. So in our notes, we're going to write next to EMF, this is constant. This is the maximum theoretical voltage. If you're talking about a battery, it's printed on the label. What's the EMF of this, Cliff? Here's the battery. Grab it. Read it. What's its EMF? It's printed on the label. Find the voltage. 1.5 volts. Okay? Now, it's called EMF. EMF is an archaic term. It stands for electromotive force. It's not a force. EMF is a term that, though, that is still stuck around, and it's saying, okay, how high is the chairlift itself? How high is the chairlift? Not how high is the mountain. How high is the chairlift? You see Callum, each battery, I have a coal that sits in a different block. Each battery has an internal resistance. It's supposed to be really small. To show that it's tiny, we label the internal resistance with a lowercase r. And as current goes through here, you would lose a tiny bit of voltage. You would lose I times little r going through the battery. In other words, the terminal voltage, this right here, is actually equal to the maximum theoretical voltage, the label, which never changes. Take away what you lose going through the battery. And what do you lose going through the battery? That voltage. I'm using I times R in place of voltage. Total current, but I'll use a little r. Actually, that's our shorthand to let us know we're talking about the internal resistance of the battery. Ideally, we'd like it to be 0. That would be a perfect battery. Sorry, doesn't exist. You know what? Have you gone skiing before? Have you gone skiing before? Snowboarding, skiing? Any snowboarders or skiers here? Okay. When you get off the chairlift, immediately as you get off the chairlift, do you go down a tiny little short hill to ski off the chairlift? In other words, you lose a little bit of height just exiting the chairlift. That's what the internal resistance is. It's that little bump getting off the chairlift in our ski hill analogy. The chairlift is the EMF. You never get that. In fact, in all the questions that we've been doing so far, Ashley, I've actually, in all the circuits, been giving you the terminal voltage and just not distinguishing them because you've never seen me draw a little resistor inside the battery. Go look at your notes. I've been careful to avoid that. Okay? So let's look at this again. Here's our circuit. This is the chairlift height. It's constant, never changes. It's the maximum theoretical voltage. It's printed on the label. But the terminal voltage, this is the actual measured voltage once you're in the circuit. The only problem with my analogy, Nate, of it being a little bump at the end of your chairlift that you ski down to get off is this bump can be bigger or smaller depending on how big the current is, which in real life, okay, finally my ski hill analogy totally breaks down. So, okay, live with that. If you're running a lot of current through here, you lose more going through the battery. You might only get 1.2 volts out of your 1.5 volt battery. If you're running very, very little current through here, you might only lose a half volt. You might get 1.45 volts. If you're running no current, which is if you just take a voltmeter and touch it to the ends, you're not running any current, then it will say 1.5 volts because you haven't actually activated that little internal resistor. Okay? And in fact, this is going to be sort of our equation. So, current through the cell, usually I total, unless there's more than one battery. Internal resistance of the cell, R for resistance, to show that it's supposed to be small, Claire, little r. Usually it's written right before the actual battery symbol. Sometimes it's written right after the actual battery symbol, and then it's traditional to put some kind of a little box or something around there. In fact, if you look at your ultimate review, you guys can stay in your looking at your notes, but in the ultimate review, it's pretty obvious which ones are having, oh, there. That's the internal resistance. There's the whole battery. That there is the EMF. You're really not going to get 8 volts. Now, this is a double battery. It's a bit of a trickier one. Let me find a different one instead that's a little simpler. Here, okay? The EMF is 6 volts. You're not going to get 6 volts from the battery. The terminal voltage is going to be 6 take away whatever I times R is right there. That's going to be what you're actually getting. And what I've been doing, Claire, up until now, is I've been giving you circuits that look like this. Technically, I've been giving you the terminal voltage, not the EMF. I just didn't want to get into it. Is that okay? Nope, didn't want to do that. Nope, wrong button. Come on. Okay. So, Nate, in my ski hill analogy, I said internal resistance is a little bit like that little ramp at the top of the chairlift. As part of the ride to the top cell, there is invariably a bit of a height loss on the ramp, that little bump that you get off. The only problem is, in a circuit, Alex, that bump can change its height. In real life, clearly that doesn't happen. So the analogy is finally breaking down. But it's much more accurate. Example 1. Hey, what happens to the cell voltage measured by the voltmeter if we close the switch? Well, the cell voltage, which I'll call V terminal, the actual measured voltage. Did anybody have a formula sheet? What do they call it on your formula sheet? Can you find the equation that has the little EMF symbol? I know it's got a plus or minus. We'll get into that. Do they use VAB or V term? V term. They use V terminal? Okay. Before you hook anything up, minus what you lose going through the battery. And I'm going to say, by the way, this is I total. Okay? So here's the question. When you close this switch, are you adding a resistor or subtracting a resistor? Adding. In parallel or in series? This is important. The resistor that you're adding, is it in parallel or in series? Okay, so we're going to say here, if you add resistor in parallel, R total, this is what I've been trying to say for the last 3 days now. When you add a resistor in parallel, what happens to your total resistance? Decreases. If your total resistance decreases, what happens to your total current? Increases. What? So, somehow that little ramp at the end of the chairlift just got bigger, which, again, my analogy breaks down, but it works good for everything else, so we're still using it. Okay? Turns out then, the terminal voltage decreases because the overall current increased. It says, explain your answer. I just wanted to do it next to the diagram so I could see what's going on. Now, you may say, Alex, well, it'd be kind of nice if we could get rid of that. That seems like a waste of energy. Actually, no. We're clever. We've also turned it into our advantage. It turns out this tiny bit of voltage, when I go backwards across the battery recharging it, that's the little extra bit of voltage that's recharging the battery, which is why it takes so darn long to recharge a battery, why battery rechargers are little trickle chargers. That's why it's a plus or minus on your formula sheet there. It depends on what direction you're going through the battery. We'll talk about that in a second. So it says, find an expression for the terminal voltage. You know what? Terminal voltage is maximum EMF minus what you lose there. There's another way to find it. Or, if I call this V1, V2, and V3, let's change colors, Mr. Dueck, so it stands out a bit more. If I call this V1, V2, and V3, can you see, since these are all in series, Sammy, if I added up all three of those voltages, ignoring that one, that's also the terminal voltage, because it's get off the chairlift, go down the bump. You better cancel it out with those three. So another way to calculate V terminal is if you happen to know all of the voltage going around the rest of the ski hill, That's not on your formula sheet, but sometimes that's quicker. Sometimes that's quicker. So, example 3 says, find the terminal voltage. The cell supplies energy to the circuit. So, the EMF is 20. Do I know, like before, the total current? Because that's what I want to find first. Have they told me total current anywhere? No. Have they told me anywhere with 2 pieces of information? No. Oh, then let's write this as its equivalent circuit. What's the total resistance of this circuit? Because those are both in series. And the nice thing is the battery one will always be in series. The rest of the circuit might have some parallel garbage, but the battery, the internal one, it's always going to be in series. Okay? So you're telling me total resistance is 32. Oh, and total voltage is 20. What's total current? Total voltage divided by total resistance. And our symbol for EMF is that little funky curly E, the Greek letter epsilon. 20 divided by 32. How many amps are coming out of this battery? .625 amps, which means right here I have 0.625 amps. Cliff, it means right here I have 0.625 amps. Oh, and more importantly, is that someone's phone? Did I hear something beeping? Elijah is trying hard to keep a poker face. Was that Elijah's phone, Hakeem? This is your... Was? Wow. Elijah, thank you so much. Wednesday, at the end of the day, some Timbits. You got your phone out? Not your phone? Got to prove it. So, back to here then. It looks like what I really have, the terminal voltage is, how high is the chairlift? Look up, look up, look up. 20 minus, what do I lose on that little bump? I times R. Right? That's the terminal voltage. The other way I could have done it, like I could have said, you know what? Since this is the only actual ski hill, that must be how high the terminal voltage is as well. If you go 30 times 0.625, I think you'll also get 18.75. Check it. Try it real quick on your calculator. Yes? So I got a couple of ways I can find this. As a formula, I would say, okay, terminal equals the EMF minus I times R. It's going to be 20, the maximum. So this battery has a 20 printed on the label. Whatever circuit you hook up to, the EMF never changes. That's 20. It's a constant. Minus the terminal voltage in this case is 0.625 times 2. Looks like the terminal voltage is 18.8 volts. I'll go to 3 sig figs. But again, Alex, conveniently, had I known the voltage here, I could have just assumed that that was the terminal voltage because that's the only ski hill that we went down. So we're modifying our analogy. Aaron, ski hill is actually the height of the chairlift minus the bump. As opposed to, we used to just say, how high is the chairlift? Now I have to say, how high is the chairlift minus the bump? Oh, and Manisha, if they don't give me an internal resistor, then they've given you the chairlift and the bump included. Find the terminal voltage and the internal resistance here. Oh, this one's going to be even easier. Did they tell me total current? How many amps are flowing through here? Is that the only ski hill in the entire mountain? Is that the only resistor, aside from the internal, is that the only resistor? Then you know what? I'm telling you it's going to be 30 times 30 times 1.5. The terminal voltage is going to be 45 volts. But let me prove it with the actual equation. We said V terminal is the maximum minus what you lose. What's the maximum? What's the EMF? 50 minus I times little r. Oh, they didn't give me I times little r. I couldn't use the formula. Wait a minute. They want me to find the formula. I can, because I know V terminal. I know that V terminal, what's the voltage through this resistor? What did we say? 45 volts. That must mean that and William, the only reason I can say it is that's the only ski hill. If they had something like this, if they had 145 volts and they had another one here of 3 volts, well, then the terminal voltage would be 48 volts. Okay? Okay. Get the I by itself, get the R, sorry, by itself. How? Minus this to this side. And then get that by itself. How? Divide by? I can't hear. Okay, I didn't hear anything, I guess. I want to get this by itself. Minus that to that side, and then how would I get this by itself? How would I get the R by itself, the internal resistance by itself? Close. Negative current. Isn't there a negative in front of the I? Okay. What must the internal resistance of this battery be? 45 minus 50 divided by 1.5. The internal resistor of this battery is divided by negative 1.5, Mr. Dueck. Ha! After all my ranting about the negative, I forgot to type it in. 3.33 ohms, yes? No yawning. Next page. Example 5 says, find an expression for the terminal voltage if the cell is being charged. Okay? Now, the terminal voltage is going to be the EMF plus IR, because now the current is going this way, which means you're actually somehow going up the hill, not down the hill. You're gaining voltage. You're gaining voltage. And it's this little bit of extra that recharges a battery, and it's never, Alex, going to be very big. And the reason it's never going to be very big is we don't want our batteries to have a big resistance when we use them, so we build them with a small resistance. But the natural effect then is I've only got a little tiny bit of I times little r that I can use extra going backwards through the battery to do the recharging. Can't have both. Well, you can. We're getting fancy schmancy new material. But our standard, lithium-ion battery, this is why it takes your lithium-ion batteries a long time to recharge. It's that little IR going backwards. That's the voltage bump that we can use to reinitiate the chemical reaction and recharge the battery, separate the charges. And that's why on your formula sheet it does say plus or minus I times R, right? Minus if you're just using it regularly, plus if you're recharging. And it'll be very obvious that you're recharging. There'll be two batteries in the system. One will be clearly bigger or be called the charger or something like that. So, find the terminal voltage if this cell is being charged. Do I know total current? Ashley says no. Is there anywhere where they've told me two pieces of information? No. Okay. By the way, I think downhill is this way, yes? For what it's worth. What's the total resistance of this circuit? Because they're all in series, yes? Is that okay, Cliff? What's the total voltage of this circuit? Really what I should say is what's the net voltage of this circuit? So be careful. 21. 21. Right? 30 up and 9 down. Is that okay, Kurt? The total current is going to be 21 divided by 11. This is going to be a decimal, but that's okay. 1.909090. I'll call it 1.91, but I'll keep this on my calculator. So, how many amps are going through this top 5 ohm resistor? 1.91. How about this bottom 5 ohm resistor? 1.91. Ooh, how many amps are going through this little 1 ohm resistor? 1.91 amps. 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 The terminal voltage, are we recharging or discharging our battery? We're recharging, so it's going to be the EMF plus that little gain. 9 volts plus 1.91 times the internal resistor. If you measured across that battery in this setup, you would not read a 9-volt battery. You'd read a little bit extra, a little bit bigger than 9 volts, and it's that little bit bigger than 9 volts, William. That's what's doing the recharging. Is that okay? This is why, if you've ever wondered, why does it take batteries so long to recharge? It's because we build them with a small resistor because we don't want to lose a whole bunch of energy going through the batteries when we just charge them. Sorry, then we only have that little I times R coming back through to recharge them. Oh, plus 9. 10.9? Yeah? Is that okay, Kelly? Okay. So terminal voltage, your actual voltage, it varies depending on what you hook it up to. EMF, does EMF ever change? It's constant. It's what's printed on the side of the battery. It's your maximum theoretical before you hook it up to anything. Usually symbolized with an E, an epsilon. So, in summary, if we're supplying terminal voltage, is that maximum minus what you lose, maximum minus the bump. That goes in that box. If the cell is not supplying current, if the cell is instead being recharged, how can we write that as one formula on your formula sheet? And we expect you, Clara, to figure out whether it's discharging or recharging. It's pretty obvious from the diagram. I think, to be honest, in the review, there's only a couple of questions where you're recharging. And I have to look, but I don't even think I've ever put it on the test. It's interesting trivia. I should, because rechargeable batteries are a bigger part of technology than they were 15 years ago with your cell and your mobile devices. But anyways, of course, the odds are in 5 years that technology would totally change anyways. Just like the TVs or some, oh, sorry. Okay. What's your homework? Number 1. I like number 2. I like number 2. I like number 2. Number 2 is a nice question. Three is good. Yeah, sure, 4 is good. 5A. Yeah. 7 is good. Skip 6. Take a look at number 8. What's weird about number 8? Do you see it? What about the switch in the middle? The switch is in the middle in number 7 as well. There's no resistor in the switch circuit. This is a short circuit. This is bad wiring. I'm just going to talk about, I'm not going to assign it. What would happen if you close this because electricity wants the path of least resistance? Now no longer will charges flow through there at all. Now the only resistor that you have is this 0.5 ohm. Your current is going to go away. In fact, if you go 20 divided by 0.5, the current just jumped to 40 amps. This is going to start to heat up. Okay, so this is why if you're ever adding switches, in fact, usually switches have a built-in resistor just for this purpose to be safe and paranoid. Yeah?
Would there actually be 0 amp capacitance to 10 ohm resistor?
Very close. In fact, in theory, yeah. Okay. In actuality, because in real life wires have some resistance of their own, yeah. Fine. But we've been ignoring that so far. Anyways, number 8 I'm not going to give you, but okay. 9 is fair game. 9 is summary of the whole unit, but no terminal voltage. Looks like 100 is the EMF. I don't see an internal resistor there. How many more do I have? Skip 10, 11, 12. Lots of practice, but you have lots of time. But I got to interrupt you guys for 1 second. So